Good evening, everybody. My name is Alex Rasmussen, and tonight it is my pleasure to be talking to you about flat data center storage. This is a paper that came out of a group of folks at Microsoft Research in 2012. It was presented at the Usenix Symposium for Operating Systems Design and Implementation, otherwise known as OSDI. It's one of the biggies in the systems world. This paper is, I'm really excited to share this paper with you because I think that it's a great example of what a scalable data system design looks like when it's really well thought out and executed flawlessly. I think it has a lot to teach us about ways that these systems can be constructed and kind of general overarching kind of mental frameworks that we can use to inform how we design these systems in the future. Before I start, I'd like to thank a few people. First, thanks to Fastly for providing the funding to put this together. Thanks in particular to Inez and Elaine for putting all this stuff together and doing all the logistics. Yeah, absolutely, please. A round of applause to them. This has been said by other speakers in the past, but this is really just an invaluable resource and gives a chance for academics and industrial people to really kind of exchange ideas and interface, and I wish there was more like this out there. Thank you to GitHub for providing this just superlative space to give this talk in. Thanks to the authors, first for writing the paper, and second for putting their slides online so that I could steal from them. And finally, thank you all for coming. I'm impressed and amazed at the turnout. My name's Alex Rasmussen. I'm an engineer at a company called Trifacta. Trifacta does data transformation software. I like to say that we make washing machines for data, and we do it better than anybody else. If you're interested in knowing more about that, please come find me after the talk. We are hiring. I'm Alex Ras on everything, mostly on Twitter, so stalk away. Before I started at Trifacta, I was a graduate student for 6 years at the University of California, San Diego, working a lot on efficient data processing at scale. So a lot of the work that I did centered around two big pieces of work. The first one was a system called MinuteSort that sorted stuff really fast. The other one was a system called Themis that did MapReduce on stuff really fast. Between those two systems, we managed to set a few world records in sorting, which I'm pretty proud of. All of this is kind of, number one, kind of a humble brag, and number two, a great digression to the fact that I've been thinking a lot about big data for about the last 8 years. It's kind of been what I've been immersed in, and I've been looking at it both kind of from an academic context and an industrial context. And one of the things that I like a lot about this paper that we're about to discuss is that it starts by kind of coming at the problem from this very greenfields kind of stereotypical, almost academic approach of what can we do if physics and money weren't an option, and then brings that into parity with reality in a way that actually comes out looking really elegant and nice. So, given that often in technology the ideals are much more pleasant to talk about, let's start by examining what a perfect world would look like if you were a big data person, right? If you wanted to build a big data system and money and physics were not an object, what would you build? So you probably build something that looks a lot like this, right? And in this block diagram, you've got a bunch of these little guys up here, and they're processors. And their job is to take data items in, do something interesting with them, and then write data items out again. And then on the bottom, you've got these disks. And of course, disks are there for storing data and giving it back to you when you ask for it. And the processors and the disks are connected together with this thing in the middle that I'm going to call Magic RAID, which behaves a lot like RAID except magical. And I'll tell you why. So Magic RAID's got a lot of nice properties. The first nice property that Magic RAID has is that if you write data to Magic RAID, it stripes that data in really, really fine granularity across all of your disks. And the reason why that's nice is because if you've got a lot of things that are reading and writing data items off of this giant pool of disks underneath Magic RAID at the same time, you can kind of statistically assume that, number one, all of your disks are being kept busy. They've all got stuff to do. And number two, your processors are all going to get pretty good bandwidth because they'll be able to read from a high diversity of these disks at the same time. By the way, we're assuming spinning Rust and platters here, not SSDs, although there's nothing that really is predicated on the existence of magnetic disks for this work. Another nice property that magic RAID has is that the two kind of halves of the system can scale independently from one another. So if I need more compute capacity, I just add more processors. And if I need more storage capacity, I just add more disks. And conversely, I can take disks or processors away, which means that I can use, for a high diversity of different kinds of environments, this magical thing actually works. Now, unfortunately for all of us, we don't live in a world where magic RAID can exist, at least not on a single box. We live in the real world, and the real world is constrained by money. And it's also constrained by physics. And it's really hard, if not impossible, to build a single box with something like magic RAID inside of it that can scale to the kind of workloads that a company like Microsoft or a company like Google or Facebook have to deal with on a day-to-day basis. So what do we have instead, right? Well, instead we've got these, right? We've got actual physical racks of machines that are organized into rows. And each of these racks typically have a switch at the top of them, and the switches are organized together. When you get enough of these things, you actually have to do a second level of aggregation where the switches at the end of the row connect together into a core. And the way that these switches are connected together is the network's topology, right? It's the way that the network's laid out. And Sargon did a great job of kind of laying the foundations for the networking side of this, which means I don't have to rehash a ton of it. But this is what we've got, right? And CPU and disk are co-located, and they have a similar failure domain, so I can lose processors and disks at the same time, et cetera. Now, if you're in the kind of big data space and have been doing anything for the last 5 years, you've probably seen this little guy. This is the Hadoop mascot. The Hadoop ecosystem is this ubiquitous set of software systems that were originally derived from papers that Google published in the early 2000s, in particular the MapReduce paper for compute and the GFS paper for storage. And these systems were wildly popular academically, and when Hadoop picked up steam, they gained a lot of industrial traction. And as the success of those paradigms became bigger and bigger and bigger, so too rose this kind of central mantra of that section of papers, which is you have to move your computation to your data. Just show of hands, how many people have heard some variation of this phrase before? Yeah, pretty much like most of you. So one of the things that, for standard kind of tree topology networks, like the ones that VL2 was meant to replace, this makes a lot of sense, but it also comes at a cost, right? So if you want to move your computation to your data, you have to be aware of where your data is. And the awareness of your location adds an enormous amount of complexity to your system, right? And there are a bunch of different ways that that comes about, right? Because your data is spread all over the place and you have to know where it is, your scheduling algorithm becomes non-trivial now because you have to figure out, well, what do I move my computation to? Your processing model also becomes a lot weirder, right? I mean, MapReduce is a great conceptual idea, but the main reason why we're doing that and not just writing a bunch of single-threaded code is that I can take my map task, split it up into a bunch of teeny tiny pieces, and move those teeny tiny pieces to where my data is, right? Unfortunately, what we learned really quick after Hadoop got popular was that the class of things you can express with a single MapReduce job is actually pretty limited, right? And so you get this whole class of systems that either start experimenting with other stuff, which is awesome, or they start taking these giant graphs of MapReduce jobs and plumbing them together to do higher level operations. This is where you get your pigs and your hives and et cetera. So as a practitioner, as someone who's either building stuff on top of these systems or trying to implement these systems yourself, there's a lot of additional complexity here and a lot of overhead. So the researchers that wrote this paper started by asking, well, look, why, right? Why do we keep repeating this mantra of move the computation to the data to ourselves? Like, are we just repeating this without thinking, or are we kind of, we should examine the kind of fundamental principles behind why we're saying this? And a lot of you are probably going, well, like, duh, Alex, right? Move the computation to the data because remote data is slow. And at the risk of sounding like a 2-year-old, I'm going to go, well, why? Right? Why is remote data access slow? And if you follow this line of reasoning, you eventually come to the conclusion that, well, it's really just because your network is oversubscribed, right? And what do I mean by that? Well, as Sargon pointed out, the state of the art prior to these kind of close topologies with full bisection bandwidth coming out was that you had this kind of tree aggregation structure. And if two machines want to talk to one another, say machine A and machine B in the diagram that's shown behind me, they have to go all the way to the top of the tree and then all the way back down to the edge again. The problem here, of course, is that as you go up the tree, the amount of bandwidth that each member underneath that layer has, their kind of proportional share, gets smaller and smaller and smaller, right? And you can think of it like if I have a rack and the rack has 40 servers in it and I have a 48-port switch, well, I can connect each one of those computers to that switch, and then I've only got 8 ports left over, right? So if I've got gigabit links, I have 40 gigabits going up to the top of the rack, and I've got 8 gigabits going to literally everywhere else, right? And this gets even worse when you go up from the kind of second level of the network, kind of the aggregation layer up to the core, because these core switches are just stupid expensive, right? So in the paper, they say that this oversubscription factor can be as bad as like 100x or more, which really means that like even if I've got 10 gigabit links to my edge, I'm going to get a teeny tiny fraction of 10 gigabits per second between any arbitrary pair of hosts, assuming that, in the worst case, everybody's talking to everybody else. So this is when the paper starts to do like the researcher thing of like, let's get weird for a minute. So what if I told you that the network wasn't oversubscribed, right? Well, the first thing you go, well, of course the network's oversubscribed, but what if I told you that it wasn't, right? And you go, okay, well, if that's the case, well, then the world starts looking a lot more like Magic RAID, right? Because now, because your local disks and your remote disks are, like you have full bisection bandwidth between any pair of hosts. So if I talk to a disk on the other side of the network, the only additional penalty that I have to incur, assuming that I'm not network bound because I have too many disks in each of my machines, is the latency to get across the data center, which is a couple micros. But if you're talking about like spinning Rust disks, that's such a vanishingly small fraction that it doesn't matter. So for all intents and purposes, disks somewhere else and disks where you are the same, right? And if disks somewhere else and disks where you are the same, why make the distinction, right? So then your work schedulers start getting simpler, your programming models start getting simpler. You can start thinking of doing computation over these things, just taking a big queue of work and just pulling off the front of the queue until you're done, right? That'd be kind of an awesome world to live in, wouldn't it? So that's kind of the premise of this entire work, and that's what flat data center storage, which I may abbreviate to FDS to avoid running out of breath in the middle of a sentence, is. So flat data center storage essentially assumes that there is no oversubscription in your network, that everybody can talk to everybody else at exactly the same rate at all times. And what they're going to decide to do as kind of a proof of concept is they're going to build an object storage system on top of that. So here's an outline for the rest of the talk. We just kind of wrapped up talking about why you would do this. Next, I'm going to talk a little bit about what the kind of architecture of this system looks like, what the API is that it exposes to clients, the kind of guarantees and the design decisions there. I'll talk about kind of two big pieces of this work, which is how flat data center storage manages metadata, which put simply is, I need to get data, where is it? And then also how they deal with replication for availability and recovery when a disk crashes. I'll talk briefly about the kind of data transport problem and some of the issues they ran into when dealing with these full bisection bandwidth networks that are a little bit non-trivial. And then I'll wrap up by kind of discussing why I think this paper matters so much in the kind of broader data systems context. So this is kind of the block diagram for what a flat data center storage network looks like. You have clients communicate with flat data center storage through a client API that abstracts some of the complexity around the messaging layer away from the people that are actually making the calls. You got a bunch of disks spread all over your network. Each one of those disks has a thing called a Tract server sitting in front of it. And these are kind of going to be the basic unit of, like the basic worker that exists in this system. And what's interesting is these are raw disks. Like we're not even putting a file system on this thing. We're just going to take all the blocks on the disk, divide them up into sequential chunks, and just use those sequential chunks and number them sequentially from 1. And then somewhere in the network, you've got this metadata server. And a lot of people kind of go, oh God, metadata server, single point of failure. But we'll get to why this actually isn't so terrible. And the metadata server's central role is really, as the name might imply, to serve information about metadata to both the clients and to the Tract servers. So in terms of an API, Flat Data Center Storage is a blob store. So it stores a bunch of things called blobs. And as you know, blob stands for binary large object, so big block of bytes. Each blob has a globally unique identifier and a sequence of tracts associated with it. So a blob's contents are a list of its tracts. In the paper, they talk about the tracts being 8 megabytes long, but it's configurable. That number might seem a little bit magical, but it turns out that they just derived it experimentally. They did a bunch of experiments on these 10,000 RPM SAS disks that they had, must be nice, and came to the conclusion that if you have 8 megabyte tracts, that you spend enough time reading a tract before seeking to read another one or to write another one, as the case may be, that you get pretty good throughput off your disks. So there's a nice balance there. And they have a graph showing the kind of trade-off between tract size and seek time. The API that you get out of this thing is pretty straightforward, right? You can create blobs, you can delete blobs, you can open and close blobs by referring to their GUID. You can figure out how big a blob is. You can actually extend a blob by giving it more tracts. One of the nice features of this API call is that the return value of extend blob is a sequence of tracts to which you can now write. So if you have concurrent appenders are guaranteed to not collide with one another. This might be interesting if you're using these blobs, say, to store like logs or something like that. And then, of course, finally, you can read and write individual tracts in a blob, however you want. So the system guarantees that writes to individual tract servers are atomic, meaning they either happen or they don't. There's no in-between state. All of these calls are asynchronous, and that's important because if the calls are asynchronous, you assume that the client's going to do really deep pipelining of calls. So you can imagine, for example, if I've got like an 800 megabyte blob that I'm reading, I could make, if I really wanted to, 100 asynchronous read calls and just wait for all of them to come back and assemble them together. Now, of course, you probably don't want to do that because you don't want to keep an 800 megabyte buffer in RAM. But you can imagine doing kind of this sliding window thing like what TCP does, right? And that is pretty key for reasons that we'll see in a minute. A lot of these API calls are weakly consistent in the sense that if I issue 2 reads, they can return out of order. If I issue 2 writes, they can return out of order. If I write to a replicated tract, it might be that some of those replicas fail and I'll have to retry the write. For their purposes, that was okay. They talk in the paper a little bit about how you could kind of shoehorn something like chain replication or some other kind of replicated state machine approach to get strong consistency out of these APIs, but they don't, probably because none of the applications that they were looking for needed it. So that kind of wraps up the discussion of how the pieces fit together and what the API looks like. Let's talk a little bit about how you do rendezvous between clients and servers, right? How do clients figure out where tracts are? So the metadata server that I discussed a couple slides ago is responsible for pretty much one thing, and that's serving this thing called the Tract Locator table. Again, as the name might imply, the Tract Locator table is there to help clients locate tracts. So this kind of tabular format is going to get a little bit more complicated once we start talking about replication, but in its most general form, you have a bunch of tract locators, which are sequentially numbered. Each one of those locators has a version number that we increment every time we do something interesting. And then those tract locators also belong to a tract server. So you could imagine that a tract server is responsible for storing information about a bunch of different tract locator tracts. So how do you go from a blob with a globally unique ID and a tract number to the tract locator number in the table that you need to use to figure out what server to talk to get it, right? Well, you use this formula. It's pretty simple. You take that tract locator table, you hash the globally unique ID, add the tract number to it, and then you make sure you don't overflow the table by just modding by the length of the table. So each piece of this is kind of important by itself, and these were all arrived through, I'm sure, a great deal of blood, sweat, and tears on behalf of the people that were building this thing. The first interesting thing about this is the hashing the globally unique ID. And this is really to make sure that even if your globally unique ID space is somehow clumpy, right? Like it's not evenly distributed throughout the entire space, that the assignment of blobs to servers is going to be as random as you can possibly make it. And they just use SHA-1 for this. You could probably replace this with your favorite hash algorithm and be fine. Another thing to notice is that they don't add the tract number inside the hash, they add it outside the hash. And this is actually, they say this is something that they didn't expect to have to do at first. But an interesting thing is what this does is it makes sure that, especially if you have a really big blob, that it's spread over a ton of different tract locator entries. So say, for example, the hash of my GUID is 5. My tract numbers are going to locator 5, 6, 7, 8, 9, 10, et cetera, right? If you were to do this inside the hash, it's kind of hard to tell whether or not the resulting assignment of tract locator entries to tracts is going to be such that you don't have one server that's responsible for the majority of the tracts in your blob, so you can't take advantage of that parallelism. Another kind of fun thing about this is that blob metadata, information about how big a blob is, for example, is also stored in a distributed fashion across all the disks in the network. And the way they do this is they say there's a reserved tract number, tract -1. And if you want to know where the metadata is, take the hash, subtract 1, look it up, and there it is. So this is nice in a sense that you don't have, the metadata server isn't a single point of failure for blob metadata. It's not like if, for example, in HDFS, you lose the master node, you're just screwed, right? You've got a bunch of nice paperweights. So yeah, that's how you go from having a tract to having a tract locator number. So how do you construct this thing? Well, it turns out that's actually fairly straightforward too. You just take the list of all the tract servers in the world, you shuffle that list, and then you do that n times, and you concatenate those lists together, and then you number them sequentially, and you're done, right? And this essentially assumes that if you do m permutations, right, that every tract server is going to be responsible for m entries in that table. If you have disks that are of different speeds, and in the evaluation they do, they've got some 10,000 RPM disks and some 7,200 RPM disks and so forth, you can actually weight the number of times that a tract server occurs by how fast its disk is, which gives you the ability to do things like, say, faster disks have more stuff in them or something. It really doesn't matter in terms of details, but you can pretty much do whatever you want for that weighting. The tract locator table is served to clients by the metadata server. But what's important to notice is that every entry in this table doesn't depend at all on the set of blobs that are being managed by the system. They only depend on the set of servers, the set of tract servers that exist in the cluster, which means this thing is stupidly cacheable, right? Because it only ever changes when the kind of population of the cluster does. And especially if you're dealing with a relatively modestly sized cluster, you don't expect disks to come and go super frequently. So you're expecting that the load on this metadata server is going to be pretty low. So once you've constructed this thing, how do you actually add tract servers to the cluster afterwards? Well, it turns out that all you really have to do is pick a bunch of random tract locator entries and steal them and give them to the tract server that is joining the cluster. And this happens in 2 phases, right? Because you actually have to copy some stuff from the old guys to the new guy. The first is this kind of pending state where I pick a bunch of entries that I can steal, I steal them, and then I mark the entry as pending. And for each one of those entries, I increment its version number. And these version numbers, I should point out, when a client asks a server for something, it attaches the version number corresponding to the tract locator entry, which allows the server to kind of look at the version number, compare it with its own, and if they don't match, it can just go, nope, and the client can go back, grab the tract locator table again, and retry with a new version to whatever server happens to be there. So incrementing the version number helps you with that. While you're in this pending state, any read requests to tracts managed by that, or for that tract locator entry, go to just the old owner, right? So for tract locator entry 1, they would just go to A. But all writes go to both the old guy and the new guy, so A and the new server at the same time. What this ensures is that the old server has the authoritative state of all of the blocks that are managed, or all the tracts rather, that are managed for that tract locator entry. The new guy has some fraction of that. So as long as you can keep the new guy up to date on writes, then as soon as the new guy is done copying everything from the old guy, you are sure that the new guy has all the state that the old guy should have had. And that's actually what happens next. So once the copying's done, you can essentially say, okay, now the update is committed. I can get rid of the old tract server's entries. That tract server can garbage collect the portion of its state that corresponds to that tract locator entry. And now you have more servers, and you can do this as many times as you want. They go into some details that I won't cover here about what happens when you've got concurrent ones of these things happening, and what happens if something fails in the middle of a migration, and so on. So we talked a little bit about how you figure out where your tracts are. Now let's talk about how you keep from losing data when something fails. So classic way of doing that, you store multiple copies. So in a replicated situation, the tract locator table looks pretty much the same, except instead of one tract server being responsible for every table entry, you've got some number. In this example, I've got 3. And one of the things that's nice about this is that you can have variable replication in this system. If you say in the blob's metadata, how many replicas should I have? And then you just take the first n replicas in this table up to the maximum replication amount. So that gives you some flexibility there, which is nice. One of the things that they kind of recommend and do for their evaluation is that they make sure that every pair of tract servers appears in this replicated table at least once. And you might ask, well, that means that the tract table is going to get really, really big, right? Why did they do that? Well, if every pair of tract servers is represented, then that means that data that is owned by a given tract server is going to have a huge diversity of other tract servers that hold replicas of the data that it has. And this becomes really important when we start talking about how recovery works. So you might ask, like, okay, well, I've got this kind of every pair is represented. I can add more replicas. How do I pick which replicas I should be using for each row? Well, you can do it at random. And I'm not entirely sure if that's what they did for the evaluation. But they also point out that you can actually do custom failure domain specifications. So for example, you probably don't want all 3 replicas to be inside of the same physical machine, because if its power supply explodes or the rack it's in melts, you're done, basically, right? Because you've just lost all your copies. So they say, they don't go into a great deal of detail about how you specify these things, but you can specify them. So your API operations change a little bit in the face of replication. In particular, you have to make sure that some of your metadata operations happen in the right order so that you don't get confused about how big your blob is or whether it even exists. So if you create, delete, or extend a blob, which are kind of the things that modify the state of a blob, you actually deal with a kind of primary backup system, right, where you do the write to the primary 2-phase commits to the other replicas, and then only returns to you once that 2-phase commit finishes, right? So you're sure that when that call completes and comes back to you as a client, that all 3 of the replicas of the blob's metadata state know that that metadata state is the same. When you're talking about writes, you have to do a write to every single replica and only return to the client when all of those writes complete. That makes sure that all of your replicas have the same value. As I mentioned before, weak consistency here, so the API may come back and say, try the write again because I couldn't talk to the 3rd guy. And you may actually have to wait until that 3rd guy recovers sufficiently. But there's nuance there. When you read, you can read from anybody at random, right? Because you're sure that your writes are going to be the same. And if you read from a random replica, then you can kind of spread the load out, right? So that's nice. So what happens when a tract server fails in this kind of a scenario? Well, the first thing you have to do, and I'm going to say that A fails here just because it occurs a lot in the table. You have to go through your tract locator table and you have to take every instance where A occurs, you have to delete that portion. and you have to replace it. Well, interestingly enough, if you're used to something like RAID, you might have this notion of like, if a disk dies, I have to replicate that disk somewhere. And here, you don't really need to do that. You just have to make sure that every tract that disk stored is in this case, 3 places. And you don't really care which 3 places because data locality isn't a problem, right? So I just take all the entries where A occurs, I replace them with random things. I just realized I replaced A with A when I was trying to be clever. Ah, stupid. Anyway, once you've done that, you pick another replica, and you can pick that other replica at random, and you say you are the replica from which the replacement will restore all the tracts that A had for this tract locator entry. So what does this mean, right? This means that when a disk fails, what you're going to see is a bunch of different tract servers talking to a bunch of other different tract servers all at the same time, frantically trying to replicate all of the tracts that tract server had back up to the full replication rate. But what this means is that instead of a situation where you had 1 or 2 disks that you had to sequentially read from to do a restoration, like if you had a RAID 5, you got to go all the way through and it takes like a day. This thing can recover from the failure of a terabyte disk in a 3,000 disk cluster in about 20 seconds or less, right? And this was the part of the paper at which my mind is just blown, right? Because you look at that and you say that by itself is justification if you're talking about a highly available blob store, right? Because your biggest fear when you're dealing with replication is that the time that it takes you to recover will be longer than the time that it takes you to fail enough that you lose data. And if your recovery time's that short, I can just go around like pulling disks out at random merrily, and it probably doesn't care, right? This thing is like the honey badger of object storage systems, right? So this by itself should just make you go like, holy crap, right? So now that we've talked about how you do replication, how you do recovery, let's talk a little bit about some of the problems they ran into with data transport, which really is how do I get tracts from servers to clients and back again, right? So as Sargon pointed out in the previous talk, this thing assumes a full bisection bandwidth network. In particular, it assumes something that kind of looks like this, where you've got a lot of path diversity and a lot of tiny commodity switches. And if you wire together your tiny commodity switches in just such a way and you use ECMP to make sure that you can use that diversity of routes, you get full bisection bandwidth, right? That's nice. And you can do this at data center scale, right? Even better. There are a couple gotchas, though. The first gotcha is that I have to make sure that there's enough networking bandwidth at each of my machines so that my disks aren't bottlenecked by my NIC, right? So what do I mean by that? Suppose that I've got a disk that's a 10,000 RPM disk. You can probably get about 1 gigabit per second of sequential bandwidth out of that disk, kind of best case, right? If I have a 10 gigabit NIC in my machine, I can put 10 disks in that machine, and that's pretty much it, right? Past that, my disks won't be able to go at full speed because they'll be bottlenecked by the NIC. So that's the first thing. The second thing is that the full bisection bandwidth that these kinds of topologies provide isn't guaranteed. It's stochastic. It's statistically likely, right? And in particular, it kind of relies on being able to deal with an enormous number of these really short flows in order to provide that statistical guarantee. Now, ECMP, equal cost multipath routing, really likes short flows to random places because it gives it this diversity that lets it spread things out across all this path redundancy that it's got. Unfortunately, TCP hates short flows because TCP needs to ramp up to figure out what its bandwidth is supposed to be, and if you're not giving it that much data to transfer, it won't know. There's also this horrible thing called incast, which I don't have enough time here to really do justice to, but the bottom line is it's terrible and it causes your TCP throughput to collapse to essentially 0. The thing that's nice about flat data center storage, though, is that because they have full bisection bandwidth, problems like incast don't happen somewhere in the middle of the network where you can't really do anything about it. They tend to happen at the edges. They tend to happen at the individual machines themselves. And so what you can do is you can actually implement an application layer solution to this problem. What they do is this variant on this thing called RTS-CTS, which in a nutshell really is, before I ask you for something, I'm going to ask you if you've got enough capacity to give it to me. And you're allowed to say no. And if you've got enough capacity, you send what's called a clear to send message, which says, yeah, go for it. But you're only allowed to have a certain number of these things in flight at any given time. And that prevents you from the situation where everybody asks you, can I get a tract from you? And you say, sure. And then everybody goes, give me my tract. And you've got a giant queue in front of you, and your TCP connections time out and reset before you can service everyone. So this has been the whirlwind tour of flat data center storage. I'd like to spend some time, though, talking about why this paper, I think, is important from a data systems perspective, from a systems perspective, from a general philosophical perspective. I think that this paper is a great example of what I like to call co-design. Now, co-design is when you consider your hardware and your software and the workload that that hardware and software is supposed to do as kind of three corners of a nice beneficial triangle. And you design something that works really well if all three of the points on that triangle are constrained, they're fixed. But if any one of those points starts to get fuzzy, then maybe some of your assumptions kind of start to fall apart, but that's okay, because you know exactly what you're building, you know exactly what you're building it for, right? So flat data center storage is a blob storage system. It's designed for full bisection bandwidth networks. And it works great for that workload. And there are a bunch of evaluations in the paper showing how it scales and so on. I'm going to focus on one particular piece of evaluation because it's personally relevant, and that's their performance against the sort benchmark. So the sort benchmark is this thing that is this collection of benchmarks that measure sorting as kind of the yardstick problem in data systems. And this was originally developed by the late Jim Gray, one of the demigods of database systems, as a way of kind of figuring out if you can pick a really hard thing that a data system like a replicated database has to do, but one that's really easy to actually describe, sorting would be a great example of that, right? Because you got to read a bunch of stuff, you got to move stuff to where it needs to be locally sorted. You have to do some non-trivial computation on it, i.e. sorting it. You got to write that stuff back down to disk in sorted form. You've got to do all that stuff all at once, all the time, as fast as you can. So this really puts a stressor on any data processing system, really. There are a bunch of different benchmarks here, like dealing with energy efficiency and capacity and raw speed, but they all come in one of two general flavors. And the first the flavors are named after kinds of cars. So there's the Indy flavor, and I didn't know this before starting on this sort of thing, but Indy cars are not practical, drivable vehicles. They're designed purely to go really, really fast. Like you wouldn't want to go to the grocery store in one of these things. Whereas Daytona, like you're talking about cars that are actually drivable that you've just really souped out, like, and just made as fast as you can possibly make them. The analogy is direct to systems. So systems in the Indy category are allowed to kind of cheat, and they're allowed to be really, really specific for the task at hand. Daytona-style systems have to solve a broader class of problems, and that typically deals with things like record sizes and data distribution and so forth. So flat data center storage competed in one variant of this called MinuteSort, which is how much can you sort in a minute. And it competed in both categories, and it won both categories by a pretty substantial margin. So in the Daytona category, it was competing against the venerable Hadoop. In particular, it was competing against a cluster that Yahoo put together in 2009 of about 1,400 machines. And Hadoop was able to sort about 500 gigabytes of data in a minute, which if you look at just that raw number, you go, wow, like 500 gigs in a minute, nice, right? But if you divide that by the number of disks in the cluster, the throughput turns out to be about 3 megabytes per second per disk, which is, really a shame considering, how fast those disks ought to go when they're being driven at full speed. Flat data center storage, on the other hand, they had a cluster of 256 machines, and they were able to almost triple that number. So that brings their per disk bandwidth up from 3 megabytes a second to 46 megabytes a second. And the perfectionist in you might say only 46, right? But they are reading and writing these disks at the same time, right? So you figure divide by 2. Now in the Indy category, they competed against my thing, and they won by a good amount. They won by like 10%. We had a little fewer machines than they did, so our compute efficiency was a bit better. But to their credit, both they set this number, and they did it with a sort application that was a very thin shim on top of this general blob storage layer. So whereas we spent a long time building a thing that sorted and sorted only, they did a thing that did blob storage, and sort happened to be this really simple app that they built on top of it, which was really just read all the objects, sort all the objects, move the objects to the right place to aggregate them, and then write them back down. So it's really good at what it does. I hope I've proven that. But it's important, it's as important, I think, to talk about what flat data center storage is not as it is to talk about what it is, right? Flat data center storage isn't really built for networks that are oversubscribed, right? If you stuck this thing on a standard, quote unquote, standard data center network circa 2012, where you had that factor of 100 to 1 oversubscription, it probably wouldn't do that great, right? Because a lot of its assumptions are predicated on this fact that your remote disks and your local disks are the same. It also doesn't try to be more than an object storage system. This thing isn't a database. It's not trying to do anything more than loading and storing big binary objects. But the key here is that by constraining the workload, by constraining the hardware, and by building the software based on those constraints, they were able to get huge, huge, huge efficiency gains, right? And I feel like I've kind of talked a lot of trash about MapReduce, but I think that MapReduce is another example of this when viewed in the right way. So if you look at MapReduce and GFS, they came out of Google in the early 2000s. Google was not nearly the giant corporation that they are now. They weren't small, but they were kind of scrappy. They needed to store a few copies of the internet on some machines, and they didn't want to immediately go bankrupt by doing that. And so the only solution that they could come up with was, let's buy as many cheap, crappy PCs that are going to fail all the time as we possibly can. Let's wire them together in a standard tree topology, and let's do bulk synchronous processing on those things. Suck the internet in, do PageRank on it, spit the PageRank graph out, suck iteration I in, spit out iteration I plus 1, repeat until I have the thing that goes into Google search, right? Now, if you look at this from constrain the hardware, right, thousands of cheap, crappy PCs, constrain the workload, bulk synchronous processing, the system that they came up with works really, really well for those two constraints. But what you see a lot of, unfortunately, is people who will buy $10,000, $4,000 Dell blades, not to pick on Dell, with dual redundant power supplies and liquid cooling and RAID 6 and all this stuff that make them really, really reliable, and then only have 10 of them, and then run the exact same thing that was designed for 10,000 machines that are going to catch on fire any minute. Similarly, a lot of the success from Spark kind of comes from this fundamental assumption that MapReduce just wasn't designed for iterative workloads. It wasn't designed for OLAP. It wasn't designed for a lot of these things. And that's OK, because it was what it was designed for, it's incredibly good at. Spark comes in and says, well, actually, if you wanted to constrain for an iterative system or an OLAP system, here's how you would do it. And they actually end up doing it really, really well. So what can we learn from flat data center storage? The first is that it's a great example of doing a ground-up rethink of what an architecture should look like based on a fundamental assumption. But it's great because it's ambitious. It's really ambitious. But it's also like, I can envision actually sitting down and buying the parts and building this thing, right? And that differentiates it, I think, from a lot of work that tries to do these ground-up rethinks but ends up having some fundamental linchpin that it turns out makes it unimplementable. The other thing is, again, to harp on this co-design idea, they optimized like crazy for their hardware and their workload, and they got a big, big bang for their buck out of it. And the last thing, if you were to pitch the abstract of this paper to someone, even in 2010, they would tell you that you were crazy, right? They would say, there is absolutely no way that you can get a 10 gigabit per second full bisection bandwidth network up to that scale. It's cost prohibitive, it can't be done, the hardware doesn't exist. Well, it turns out 2 years later, not only did the hardware exist, it was cheap-ish, right? I mean, it only cost them like 30% more per machine than it costs Yahoo for that Hadoop cluster. But, we're talking like a 6 or 7x improvement there, right? Like, that's a pretty big return on your investment. So I guess, like, one of the things that's nice about this is that, it reminds you, both as a practitioner and as an academic, to constantly be questioning all of these assumptions that you feel like are the gospel truth of wherever you happen to be. Because tree topologies were like a gospel truth of networking for 20, 30 years. And suddenly they weren't anymore. So I'll end with a very brief shameless plug. Another reason why I like this paper is that it resembles in spirit a lot of the stuff that I worked on in grad school. We also assumed fully balanced architectures in the sense that our disks were a bottleneck. We also assumed a full bisection bandwidth network, although unlike Microsoft, it was because we could only afford one 10 gigabit per second switch, so we had full bisection bandwidth on that switch. The whole work is predicated on the fact that you probably don't need really fine-grained fault tolerance in MapReduce if you've only got 50 machines, because your machines are a lot less likely to fail on average than if you had 10,000 of them. So what happens if you get rid of the ability to not completely restart a job if it fails? And we, as I said before, we got some pretty big wins out of this. The papers are, one of them was published in an SDI same year that FDS was. The other one was published in the Symposium on Cloud Computing the following year. With that, I am done. Thank you for your time and attention. I am happy to take any questions. Thanks. Yes. Wait. Oh, wait. I'm sorry. We're waiting for microphones.
Yes. Okay. You take the front. I'll take the back. Oh, sweet. So I'll take this section and you take the other one.
Hooray, pipelining.
Hello. Oh, God.
Hello.
Thank you for an excellent talk.
Thanks.
I would take issue with one of your later slides where you said two things. One, GFS isn't suitable to build an OLAP system on. And kind of by implication, you said that FDS may have been a good target environment for OLAP. And correct me if I'm wrong there.
I don't necessarily, so I may have sounded more doctrinaire than I actually am. Clearly, you can build OLAP systems on top of GFS, right? Like, I mean, Impala exists.
I know.
I don't necessarily, I mean, in fact, that was one of the things is like flat data center storage, it is an object store, and that's pretty much it. Like, you can build a file system on top of this thing, and they did, and it performs really well. But I wouldn't build OLAP into this thing, right? Like any more complicated interface, I feel like would just kind of, it'd complicate things too much.
I don't mean so much build it into the system. I mean, the system is a nice abstraction. Excuse me, but if you're using network bandwidth for that initial disk read phase, you're not making that bandwidth available to later phases in your execution tree. So say you're doing a typical kind of two-stage join and then aggregate. You actually need that network to do the shuffle after the fact. And if you're using it for the initial scan, you're necessarily kind of blocking out other workloads that may be running at the same time.
I see what you're saying. Yeah, I mean, I think that you could, in the example that they provide, they're basically saying it's all blob storage all the time, right? And that you're not really dealing with any other kind of data transfer really other than getting the blobs on and off. You could imagine if you wanted to read and write that stuff from disk, just doing it all disk to disk, right? But that seems kind of inefficient. You might also imagine, in a multi-tenant scenario, you could deal with not having like a 10 gig NIC with 10 gig non-blocking bandwidth all for disks. You could maybe reserve enough additional capacity for that excess traffic. I'm kind of ad-libbing here, but like if you took the density of your disks in your network down, you could probably get enough spare capacity that you could have both of those things operating on the same network fabric without having either of them stomp all over the other one.
It seems like a good idea, but then you do necessarily just get lower disk throughput.
Yeah,
these workloads are typically kind of scan bound.
That's the thing, right? Like you really kind of like, there is this fundamental, I mean, if you were really, really crazy, you might be able to build like a data network and a compute-to-compute communication network and just layer them on top of one another, either physically or logically, right? And you might be able to get something nice out of that. But I mean, it'd be an interesting thing to look at for sure.
Okay. Thank you very much.
Thanks.
So I have two things. Okay. The first thing in response to Henry's question, Facebook recently put out a paper called, or a paper basically that does TDMA over data center networks to solve this exact problem, because they actually moved to a non-data local compute scheduler for Hadoop, and they started to run into the problem where they were generating too deep queues and they were breaking their compute. The question that I had was, a couple of years ago, Berkeley AmpLab came out with a statement saying that data center or disk locality and data center computation is dead. Would you agree with that?
Well, I think the classic cop-out answer is it depends, right? I think it depends a great deal. I mean, if memory serves, and it's been a while since I've read that paper, but the premise of their argument, correct me if I'm wrong, is that because the bandwidth to remote disks is so high now, because networks are so good, and because the latency of the remote path versus the local path is not different by enough to matter, why do you care whether the disk is here or somewhere else? I think that's an interesting idea. I wouldn't go so far as to say that disk locality doesn't matter and has been replaced by memory as kind of a lot of that I think was, it's clear that RAM is getting a lot cheaper. I don't think it's cheap enough at this point to be talking about it being a replacement at scale for the kinds of things that you deal with in a data center. The thing though is that a lot of use cases, and the vast majority, let's be honest, of companies are never really going to hit that scale, right? And so in that case, like, and RAM Cloud's based around this, Spark's based around this whole notion that why don't I just keep everything in memory? It's so much faster. And that's been a really cool trend, I think, in the last couple of years in systems. And it'll be interesting to see where that goes. But I don't think the locality issue is really ever going to go away. It's just going to slide up and down the memory hierarchy.
Thanks.
No problem.
Yeah, I basically had the same question as the previous person. I was going to ask about the importance of locality for in-memory or SSD-based workloads, but you sort of touched on that already. Like, locality does still matter if this is true, because you are essentially oversubscribed on your network.
Well, I mean, I think that with locality, at least, again, ad-libbing, locality seems to matter more the faster your storage layer gets, right? If you're talking about SSDs or PCI-attached flash, like, it could very well be that the latency of going across your network actually is a fairly decent fraction of the latency of your actual operation. So you may actually want to view those two things separately. Again, it really depends. Like, if you're talking about something that's, that's throughput bound, locality probably doesn't matter to you all that much. If you're dealing with something stupendously latency sensitive, then maybe you want to direct something so that it's going to take the shortest possible path between where it is and where it needs to go. I don't know if I've answered your question, though.
Yeah, sort of. I mean, I work on HDFS, and in particular, we add in-memory caching to HDFS for actually Impala, because many of our customer workloads do fit easily in cluster memory. And
right.
In that situation, you really want to be local to the memory, because you can zero copy read it at gigabytes, like 10 gigabytes per second, which you just cannot do over network. So you get, order of magnitude improvement in your scan rates by co-locating.
Absolutely. I mean, and that I think, coming back to that key realization, right, that most of your workloads at the kind of cost per gigabyte of RAM they might fit in RAM, right? And a lot of this stuff kind of is predicated on that guess, right? And it seems to be backed up. There's been a lot of really successful work, both, and Paul is a great example of this, where you can get the scale of HDFS, but if your working set is really, really small, you can also get the latency of one of these in-memory systems. You can kind of have your cake and eat it, right? It's a nice nice trade-off to have.
Yeah, just
Almost
in general,
dropped
I
my
sort of
thing
feel
off.
that the storage world's moving to a more tiered situation where you have, we're talking about having like maybe even memory on the CPU now, right? So that's like super fast,
Right.
even faster than RAM. Then you of course have SSD, and then like disk is sort of your last resort. You almost never go to disk if you can avoid it. And that's sort of how I view things going forward, right?
Yeah, I mean definitely like the whole memory hierarchy thing. You know, there just get to be more layers, and the top layer gets faster, and there are interposition things in between, right? So you know, you even look at things like flash cache, right, where you've got SSDs caching disks, and then RAM caching SSDs, and then caching RAM, right? So you know, I feel like that's kind of always going to be there, at least as long as the memory hierarchy keeps looking the way that it does, which it may indefinitely. We don't know.
Thanks.
Hi. As someone who's sort of less familiar with the history of this stuff, I was just kind of curious what the chicken and the egg here was. Like, what was the order of like this work versus these full bisection, you know, networks and.
So if memory serves, the full bisection bandwidth literature started appearing in NSDI and SIGCOMM like 2007, 2008 timeframe. And this was released in 2012, which means they probably started working on it like 2010 timeframe. So I would say the networks definitely came first. But you know, like it is kind of this chicken and egg thing where they had data center workloads that they were having a lot of trouble with, hence full bisection bandwidth. And then they just started looking at those workloads one at a time and went, what can I do with this now? And flat data center storage kind of came out for the blob storage case.
Thanks.
No problem.
Over here.
Oh, hi.
This might be a naive question because I just haven't bought hardware in a while, but you mentioned that they got, they achieved results with commodity switches and
That's right.
some other thing implementing ECMP. I was just curious about the mechanism, what they used to build that.
Oh, like what was it built out of?
Yeah.
I don't remember the actual vendor that they got these things from, but you can, at least when we got these 10 gigabit per second switches, they were, you know, you could get a 96 port 10 gigabit switch for about 25 or 30 grand, which in the data center switch kind of market is a little bit expensive, but it's not like exorbitantly expensive. I think that they built that network out of 48 port switches arrayed together into this topology. They say in their talk, which their original talk is online, so I'd encourage you to watch that too. But they say in their talk that they made a vendor that supplies 10 gigabit per second Ethernet cables very happy. So they bought an enormous quantity of them and a bunch of 48 port switches. But
So do the switches already implement ECMP, or was that?
it's all they're all just standard Ethernet switches. It's just they're going over SFP plus cables instead of standard Cat5.
Okay.
Maybe I haven't completely answered your question.
Yeah, that's all right. I'll go read the paper.
Okay, well let's take this offline for sure.
If I could ask you one other question.
Oh, please.
So I was just curious about when you're describing the mechanism and the networking, and you have an RTS, CTS, and you have ECMP, which is establishing a flow. It's starting to look a lot like ATM circuit switches.
That's interesting.
So I was just curious if there was any comparison made to that.
Well, you know, everything old is new again, right? Like, I don't know. I mean, I think that I admit not being stupendously familiar with the kind of current state of the work in this space. I think Sargon's probably a lot better person to talk to about this than I am. But yeah, I mean, like, once you start talking about like reservation for flows that are really short, like it starts looking a lot like those kind of systems. And whether or not they actually went back and rediscovered, or not rediscovered, but like re-implemented a protocol in this context is interesting. I mean, one of the things I know that has been done in this space is that they take long flows and actually put them over circuit switched optical links. And there's a paper that a friend of mine at UCSD did that will actually dynamically balance those large flows onto these circuit switched optical paths, which looks very much like kind of like a classic telecom solution to the problem. But it turns out that if you get those elephant flows off your network and you allow the mice flows to balance, that you get a lot of nice properties out of that. So yeah, I mean, I think there's a lot of stuff from kind of the early days of packet switched networking that can really be applied here. Yes.
So I had a question about some of the replication techniques that they use in this. It seems sort of like, I mean, I don't think the replication scheme is actually the most important part of this paper, but they do include an entire section on it.
True.
It seems like they assume almost a fail-stop kind of failure scenario
Yes.
in almost every single strategy they have. And so for production systems is actually not sufficient. And so I didn't know if there was any follow-up research that you knew about where they've gone and expanded upon this, because that seems like the logical next step if you were to productionize this.
Yeah, that's for sure. I mean, like they never really, unfortunately, a lot of this work, like especially academic work, just kind of sweeps failures that are not fail-stop under the rug. And they just kind of, because when you say that a write is atomic, it's like an 8 megabyte write. Like, how are you sure, right? Like, did they actually go all the way down that road, right? And then similarly, like, what if a Tract server fails by just belching random requests across the network at random, right?
Well, and I don't even think they handle like partition scenarios, right? Because they say if a failure goes
Oh,
down,
yeah.
if it keeps talking to a client but not the metadata server, that's totally unhandled, as is the scenario where the whole thing, sorry, I just totally lost my train of thought. But the point that you were on before is it's interesting that they assume fail stop and like the whole metadata server thing too. They're sort of like, well, maybe Paxos will solve this, but right now we just like wake someone up if it fails.
Yeah, the thing, like, they very much kind of don't even like consider partition tolerance as a thing, which is kind of odd, right? I know that, so in NSDI 2014, they did this system called Blizzard, which is a file system on top of flat data center storage. And I don't know if they've actually productionized it, but from what I understand, they at least hooked SQL Server up to it and let it go. And I would imagine that SQL Server would be incredibly unhappy if some of this stuff happened, right? So, I mean, a lot of this stuff that goes into MSR, like, they're really aggressively trying to tech transfer it out. But I have a feeling that when they tech transfer it out, like, one of the first things they have to do is spend like another 6 months to a year, like, re-examining all of these things in light of like actual scale out production models. I mean, the other thing to keep in mind here too is like they've got some mitigation strategies even for like the size of the Tract locator table in a replicated scenario, right? Where if you get to above, like, I forget what the number they gave was, but it was like 5 or 10,000 disks, this thing gets so big that you just can't even hope to store it. And they talk about all these different mitigation strategies, but it's kind of like evident from reading the paper that they kind of like, they whiteboarded a lot of them and they never actually sat down and like made them work at scale.
Which, yeah, and I think is totally fine for this paper because it's like
sure.
the seminal piece in this field, right? And then I think, like you said, Blizzard was the follow-up piece,
Yeah.
right? So like that might be interesting to look at to see where they've gone.
For sure.
Cool, thank you.
No problem.